Okay, so now let's talk a little bit about performance issues. Okay, so what I just showed you in that previous slide is what is called a spin lock, where a thread is constantly trying to do a test and set, and it keeps spinning in a tight loop trying to do this test and set, and it finally exits this loop when that test and set succeeds. Okay, so if I assume, as in the previous slide, that there is no cache, then each test and set is extremely expensive, okay, because you're going to atomically do this exchange between register and memory. That memory access is going to be extremely slow, and so for that large amount of time you're essentially locking everybody else out of doing anything else. Okay, so it's really slow, and for high performance you want to be able to cache that lock. Okay, so we will assume that a lock can be cached. So here's processor 1, here is its own register file. Okay, and backing that up is its own private cache. So I'm going to assume that the lock variable is sitting in this cache over here. Likewise, a different thread has its own register file and has its own lock variable in its own cache. Okay, and so when you're doing the test and set, you're going to do the write inside your cache. Okay, now there's a problem with this as well, right? So here at the back is my main memory, and so there's a copy of the lock over here as well. Okay, so now when this thread tries to do a test and set involves a write into that location. Okay, so if I'm going to do a write, I have to first make sure that I have exclusive permissions. Okay, so if you assume a snooping based protocol, before I can perform the test and set, I have to put a request over here saying I need to upgrade my permissions so that I can perform this write. Okay, and so this will invalidate this cached copy, and then this one has the block in modified state. It then performs the test and set. In the meantime, processor P2 is also going to try and do its test and set, and so it also places a request in the bus saying I need the block in modified state. This block has to relinquish its control, move to invalid, put the latest value of that block over here, gets taken in over here, then you attempt the test and set, and so on. Okay, so every single test and set is still very expensive, right? It does not involve memory access, but it still involves a coherence transaction on the bus, right? And the block keeps going back and forth between two different threads. Okay, so this is also really expensive. So caching your lock is also very expensive because every test and set ends up taking a large amount of time. Okay, so to speed this up, we'll introduce yet another innovation, and this one is called a test and set. Okay, so each thread is not going to try and do a test and set right away. The first thing it's going to do is it's going to test the value of the lock. Is it currently a 0 or a 1? And if it is if it is a 1, if it means that the lock is perhaps currently occupied by someone else, then I won't even attempt to do my test and set. Okay, so I'll keep doing a test, which is just a read. Okay, and doing a read is not really going to involve coherence traffic, assuming everyone has a shared copy of the block. Okay, and so it's only when the lock is finally released that the value then changes, and then everyone discovers that perhaps the lock is now free, and then you attempt to do a test and set. Okay, so let me go through this in more detail over here. So here's what the code looks like. Okay, and let's look at what each thread is seeing. So here's the threads register file. Here's the threads cache. Okay, I'm just going to draw this for 3 processors. Here's the bus that they share, and here's the backing main memory. Okay, so these are all the caches. So let's assume that thread 1 currently holds the lock. Okay, and so the value of the lock in memory is a 1. Okay, if the lock is cached over here, it's a 1. If the lock is cached over here, it's a 1, and so on. And let's just assume that the block is currently in shared state. Okay, so now thread 2 comes along and tries to execute its lock function, and let's say that T3 also comes along and tries to execute this lock function. Okay, so the first thing they do is read this location into their register. So reading this location into a register, which is a simple load instruction essentially. Okay, and likewise this one's also going to read into its location, and it's going to check the value of the register. If it's a 1, then in that case you need not bother trying to acquire the lock, right? If it's a 1, then the lock is currently occupied by someone else. Let's just keep looping, so it goes back here. So if the value of the register is not 0, loop back up to lock again. Okay, and again try to issue a read. So now these threads, both of these threads, are in this tight read loop where they're just reading the value of this location, and while it's a 1, they will still continue to do this loop. Okay, and each of these reads, each of these test operations does not cause an operation on the bus, because the block is in shared state and all you're trying to do is a read, right? So that's perfectly allowed. Okay, so both threads are essentially spinning over here and just reading the values until the lock is going to be freed up. Okay, so then T1 comes along, and it was in the middle of its critical section. It finishes its critical section and then finally does a store of 0 into that memory location. So this guy is now trying to do a write into this location. Since it has the block in shared state, it has to get the block with exclusive permissions. So it puts out a request on the bus saying, I'm trying to do a write. I'm going to upgrade my permissions so I can do a write, and everybody else needs to see this and invalidate their cache copy. Okay, so this block moves to modified state. You go ahead with your write and you make this a 0. Meanwhile, this one goes to invalid, this one goes to invalid. Okay, and then T2 and T3 have not stopped their operations. They're going to do a test. That's their next operation. And when they do the test, they discover the block in invalid state, and that's a coherence miss. So you put out a request saying, I need to read the latest value of this lock location. Okay, and this thread is also snooping, so it realizes, yes, I have the block in modified state, you're welcome to have it. So it downgrades its state to shared, passes the value over here. The value is now a 0, so this cached value becomes a 0. Okay, and now when this thread goes ahead with the test, what it gets in the register file is a 0, which says that, oh, the lock is now finally free. This is my big opportunity to go ahead and do my test and set. Right, so this thread proceeds ahead, it gets out of this loop and then tries to do a test and set. Okay, and assuming that this value has not changed, assuming that this is still a 0, you do a test and set with a 1 in your register and you do an exchange. So you place a 1 over here. Okay, and you get a 0, which means you are now successful. You have been able to acquire the lock. Okay, also keep in mind that before you do the test and set, you have to first acquire the block in exclusive permissions. Right? Before you were just doing a read, which got you the block in S state. Now you have to upgrade your permissions. So you say, I'm trying to do an upgrade of my permissions. Okay, and that tells everybody else that you need to now negate your cached copy. And now this thread goes ahead with the write, and its test and set succeeds. Okay, so when it succeeds, it gets out of this loop, or it gets through this branch statement, and then executes the critical section. Okay, so now let's look at what T3 was doing in the meantime, right? So T3 was perhaps one step behind T2. Okay, so when it discovered its block in invalid state, and when it tried to do the test, it said, well, I need to first get the block with read permissions, right? So it placed the request in the bus, got the latest value either from memory, okay, and then it saw that, oh, this is a 0 as well. Okay, and in the meantime, what's happening, right? So in the meantime, this test and set may have happened, right? And so in the meantime, you got a message saying that T2 is doing an upgrade. So this block again goes back to being in invalid state. Okay, and then when you try to do a test and set, you have to get the block with exclusive permissions. So you say, I'm trying to do a write of this location, and you get the latest value from T2, which did the last write into that location. What you see is a 1. Okay, so this thread T3, maybe exits from this branch, it exits from the first loop, but when it does the test and set, it finds that the lock is already occupied, that there's a 1 in that lock variable, and so being one step behind has hurt me, and I've let T2 slip ahead with the lock. Okay, so its test and set is going to fail, and if the register value is not 0, you loop back up again over here and start from scratch. Okay, so the initial test just gives you an indication that perhaps the lock is free. But ultimately you get the lock by just doing the test and set. Okay, so there's still going to be a large amount of traffic generated when a lock is released. Okay, when a lock is released, everyone sees it and everyone tries to do a test and set. And so everyone tries to get the block in modified state, and so this block keeps getting shipped from one location to the next, and everyone over time realizes that the block is now got the value 1, which means the first thread to get the block acquired the lock, and everyone else has now been has now been left in the dark. Okay, so this is how the code works. As I said, it improves performance because for the most part, while one thread is busy doing its critical section, you're not generating much traffic on the network. Everyone is just quietly spinning and examining a value in their own cache. It's only when the lock gets released that all hell breaks loose, and everyone is trying to acquire the lock, and so there's going to be heavy traffic for that brief period of time. Okay, so in the next video I'll talk about a few more ways to reduce this traffic when the lock is finally released.